So when you talk about preparation, unitaries, and measurement, we've done the first two. Just to remind you though, for preparation, if you want to prepare a zero, you just add z as a stabilizer. Okay. Second part, when you want to do a unitary, you take the current stabilizer group and you conjugate each stabilizer by the unitary. So if you apply unitary u, the state is evolved like that, but each stabilizer is evolved by conjugation by u. So that's easy to update. So here, let's do a couple of examples. Here in this first example, initially the stabilizer on the left for 0, 0, the stabilizer group is generated by zi and iz. The zi is the first qubit and the iz is the second qubit. Now we apply an h, so now it becomes really useful to have a tablet, because you can just start copy pasting. It's not a big deal in this example. So now I apply h, and so that changes the first qubit. The z goes to an x. Okay. Now I apply c naught. Okay, so the c naught is going to copy the x forward and the z backward. So the x becomes an xi becomes xx, and iz becomes zz. So therefore, the two stabilizers are tensor x and z tensor z. These are generators. And of course, it's true because this is an EPR state. This prepares an EPR state. Okay. I did this before. I mean, it's just a mess. More complicated examples are just a mess. But again, copy paste makes it doable. So here, let's solve this one too, or at least part of it. So the initial stabilizers are here. I, Z, I. This is one set of stabilizer generators. Now you do one gate at a time. So copy, paste. So after the first C0 gate, the X is being copied forward. That Z on qubit 2 is being copied backward, and everything else is left unchanged because they're not involved. Okay, copy, paste. Okay, we're running out of space. So after this C0 gate, the X will be copied forward again, qubit 1. The Z on qubit 3 will be copied backward. Nothing else changes. Okay. Now we do, I don't know, let's do 2 at a time maybe. We're running out of space. Let's do this. So I do a T on qubit 1 and an H on qubit 2. So T on qubit 1 takes X to Y to Z to X. So instead of X, Z, Z, I get Y, X, X. And H on qubit 2 switches X and Z, so I get ZX. Like that. Yeah?
The T gate on the first qubit switches. Oh, I see.
X to Y to Z. Yeah. Okay, now I do. Anyway, do you see the point, right? Do I have to finish this? Okay. Etc. Yeah, so you just evolve each stabilizer generator independently, and you'll end up with, since they commute at the beginning, they'll still commute at the end. You'll see you'll have a perfectly good stabilizer group, set of stabilizers. Of course, like this can make. It's worth remembering that the stabilizer generators are not unique. So there's different generators for the same group, and so you might end up with a messy set of generators for a very nice group. can happen. Be really careful. This example, I did this last time. So the question was, this is exactly the example from last time. Give a stabilizer circuit to prepare this particular stabilizer state. And one way of doing it was to observe that actually when you multiply this guy times that guy, you get Ix, Ix, and this times this is Zi, 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 and so it's actually just two bell pairs. But another way of doing it would be by this, it's sort of like Gauss elimination, but it's sort of not, where you simplify one stabilizer at a time, just using C0 gates, in order to get the first stabilizer, say, to only involve one qubit. And then the other stabilizers, since the other stabilizers necessarily commute with this guy, they can't be non-trivial in the first qubit. They can be either X or I. So you can just reduce it to an n-1 qubit problem, and you recurse. So we did it last time. Here's a less trivial example. This is actually an interesting state. This state here, this is a 5 qubit stabilizer state. And it's an interesting one. You can double check. It's not CSS, right? So I'm mixing up X's and Z's. But you can double check still that it is a stabilizer state. Each of these commutes 1, 2. Like if you look at this guy, 1, 2. So they each anti-commute in 2 positions. So overall, each of these commutes. And if you want, you can come up with a method of preparing this 5 qubit state. Here, for example, I start by simplifying, by working on the first stabilizer. So I apply H2 and H3, Hadamard on qubit 2 and 3 to make these Z's into X's. That gives me this, and it also messes up all the other stabilizers, but we don't care about that. And then now I finish off this first stabilizer, so I do C0 from 1 to 2, 1 to 3, 1 to 4, and that will cancel off all those X's. And so I just get X, I, and these guys, yeah, it becomes messy. Not that messy, but you can go through it. But so now this first qubit is, since it's stabilized by X, I, this first qubit is just kept plus, the intensive product with the rest. So now it really is just a 4 qubit problem. Okay, so I don't know what the circuit is, but you could keep on going.
Do CSS states that get acted on by Clifford gates remain CSS states? You could easily make a not CSS state.
Yeah, I mean, right. If you have a CSS state where the X stabilizers are sort of separate from the Z stabilizer generators, if you apply a C0 gate, it copies X's forward and Z's backward, so you still have a stabilizer state, or you still have a CSS state.
Yeah. So
C0 gates leave it alone. If you apply anything else, maybe it won't.
Right.
But if you apply like Hadamard on one qubit, it can mess up X. It can mix up X's and Z's. If you apply Hadamard on all the qubits, then it's fine.
Yeah, I guess.
Because it just switches all the X's with all the Z's. But yeah. So it's true certainly. Like if this were a CSS state, then it's sufficient only to use C0 gates. Right? So observe here. I'll write that down. A different color. The CSS state can be prepared using only control not gates starting from ket plus tensor something, ket 0 tensor whatever. Remainder. So this K is the number of X stabilizer generators, and this n minus K is the number of Z stabilizer generators. So yeah, you can make these into zeros if you have Hadamards, but if you don't have Hadamards, if you only have C0 gates, you can't. And so this circuit, the way you do it is the same way that you do this. You just take the X stabilizers and you reduce them one at a time using Gauss elimination using some NOT gates. And at the end of the day, yeah, you'll be done. Everything's unentangled. So that's useful. I mean, I guess one thing to notice here is that like this procedure might not be optimal. Like there might be a faster way or a better way in some other method. It's definitely not unique. The preparation circuit is definitely not unique, and I don't know